Order here is 2L, right? L is here. Order is 2L. It's in 2L. Take L to 5, that will be 10. Okay? Have you used MATLAB with this before? So what's the next step you have to do? You have to give the beginning and the end of each of the band. Here you have two bands, pass band and stop band. And the start and the stop frequency of this band will be 0, this and that, right? So an example would be 0, 0.4. It's saying that the start of a pass band will be at 0 frequency and the stop at 0.4. And the next two numbers will be for the next band, 0.6, because of this. This is basically equal to pi, okay? 0.4 pi, 0.6 pi, and then pi will be 1. Right? When MATLAB sees this, factor is 4, it knows that it has two bands. The next step is to given the value of this band, right? So it will be 1, 1, 0, 0. That's the ideal response. 1, 1, 0, 0. So this is saying that the first one is a pass band, approximately 1. Well, I can put 2, okay? Because this is 2. It doesn't matter, it's a scaling factor. You can put 2. You just scale by 2. You can put 1 and 0 by 2, okay? And then that's it. If you don't say anything about the weight, then it will assign equal weight. Simple. So you should try, go to MATLAB today, and then choose 10 and so on. Design this, take P, plot it out. You see that it should be 1, and be 0, and 1. Have any questions here? So let me summarize, okay? So far we discussed perfect reconstruction, FAR solution. We discussed how to factorize the half-band filters into F0 and P0 and H0 to give us orthogonal, linear phase, real coefficient, and so on and so forth. Right? One thing left is how to design half-band filters. So we start with the fact that any half-band filter, we have this property when L is R for our example, for our design, right? And then we want to constrain on linear phase and real coefficient because we know how to design linear phase and real coefficient. Right? You can use Ramirez's algorithm, you can use many different algorithms in MATLAB. Designing non-linear phase, complex coefficient is very, very hard. Okay? So we're better off constrain our design freedom to a class or filter that has been done before, which is linear phase and real coefficient. Linear phase and real coefficient, for this example, we see that it will be a linear phase, there's a phase term, and there's a real quantity term. This is sum of both sides. Okay? So if we plug this into here and use the fact that L is R, the response, the amplitude response, we have these properties, which means that omega P and omega S have the same distance from pi to 2. Right? So this distance and that distance is exactly the same. And you can see that here, right? Okay. I can take half of pi and see pi to 2 minus omega P. And you put omega S minus pi to 2. I can do that. So what is pi to 2 minus omega P? It's right here. Right? What is omega S minus pi to 2? It's right there. So another way to remember is that they sum up to pi, or the edge is symmetric around equal distance around pi to 2. And therefore we have the term half band. Okay? So we show that the sum has to be pi and also a peak. The maximum has to be corresponding to a minimum. Right? And therefore deviation has to be the same. And therefore we have the same weight. very important in identity. The first one dealing with how to interchange operation of filter and downsampling. You can show that if you have a cascade of L by M, G or Z to the M, this is the same as L by M. You can prove it. And I'm not going to discuss it, but you can prove it yourself. Okay? And you see that this is LTI, this is linear but time invariant. You cannot interchange operation. But for this special case, you can. So you interchange them, Z to the M becomes this. Okay? The second one, start by L, Z to the L, same as Z. Again, in general, I cannot interchange operation. In this case, where this is a function of Z to the L, you can show that it is equivalent to this form. The third one is I have a cascade of M downsampling, L upsampling, equivalent to upsampling, downsampling. Greater common denominator in other words, M and L are relatively prime. You know what that means, right? So 3 and 4, okay. 2 and 4 is not. Right? This is the greater common denominator factor. Is that clear? So, in general, you cannot interchange this operation because they are not LTI system. However, if they are relatively prime, if M is 3, L is 4, okay, they're relatively prime, then you can interchange operation. You can prove this also. Okay, I'm leaving all this exercise for you to prove. Yes, assuming that we know this, we want to discuss polyphase. We will come back to do this many times. So I'm going to leave it, right here for now. I'm not going to be ready. Okay? Let's discuss polyphase. Okay. So let's discuss why we need this. Let's look at decimation. I have H. I have down by 2. Let's think about what is involved in this process. You've seen this before, right? This is in all 2 branches in the filter bank. The first, filtering and downsample. Filtering because you don't want aliasing, right? Is it efficient to do this way? Is that a good way to build the system? Who think this is a good way to implement or build the system? Are there any other alternatives that's more efficient, lower the cost? So let's think about it. I'm going to filtering, do convolution, and then what do I do here? Throw away every other coefficient, right? I keep 1, I throw away 1. I keep 1 and throw away 1, so on. That's very wasteful. It's not good. I don't want to do filtering